Okay, so we're back at it again. This is part 2 in our series on implementing matrix multiplication from scratch in Rust. In the first part, we went ahead and we created a relatively simple interface for just creating new tensors out of arrays. This is kind of close to like PyTorch, NumPy. That's kind of the feeling that I was going for. In this video, we're going to start implementing ops for one-dimensional tensors. So we're going to go through addition, subtraction, multiplication, and then towards the end, we're going to start implementing some more methods for our Tensor 1D class. This is just going to make the library a little bit more expressive and give us some more functionality. So if you've watched the first part of this series, originally the idea was to pass a generic type to our one-dimensional tensor object so that we could have those tensors store either integers or floats. That was the original idea. I've since come around to just forcing everything to be a 32-bit float inside of these tensors. The short answer why is because of Rust, but to kind of understand this a little bit, I think it's better to show it. Before we get into actually implementing one-dimensional tensor operations, I want to create some functionality in our package that will allow us to print the contents of a tensor to the console. This will just enable us to kind of check ourselves as we start implementing those tensor operations. Right now, this isn't something that we can do. This doesn't come out of the box in Rust. So if we try and just print the contents of this vector t1 into the console, here's what will happen. We will get an error, and the error message says that Tensor 1D cannot be formatted with the default formatter. So basically Rust is saying, we don't know what to do with this struct that you just implemented, so you need to tell us what to do with it. Okay, so here's the code chunk that we're going to be using in order to actually print our tensors out into the terminal. What's going on here is we're implementing this display trait. This display trait is what Rust is looking for when we actually call the print line macro. So by implementing this trait, we are now telling Rust what to do with our tensors. The definition here for the actual formatting function itself is always the same in Rust. This is just copy-paste, but what we want this function to do, right, is basically go through our vector of floats inside of the tensor and kind of combine them into like a comma delimited string, which we can then print out to the console. So the way that we do that is we take our tensor, that's self, we access our vector of floats in the elements field. We're going to basically iterate through it, and then for each element of that vector, we're going to convert it to a string. Then we collate everything as a comma delimited list. Basically, that's the idea. This write macro is what actually handles the printing of this content to the console. So we're just going to take that comma separated list and stick it in between brackets. That's our tensor representation. So if we go ahead and save this and then try and do another cargo run, you can see down here now we're no longer getting an error and we're printing out the contents of T1 to the console like we want. Now we can actually go ahead and get started implementing tensor operations here, now that we can kind of visualize the results of transformations on tensors. So the place to start, I think, is just simple scalar addition. So what we want to be able to do is create a new tensor T2, which is equal to our original tensor plus some scalar, right? Where we're just taking the scalar and we're adding it to each element of our tensor. In order to do this in Rust, we create another implementation block. In this case, we're implementing the add trait. And let's say that we're going to implement this for adding float 32s to our tensor. We're implementing this trait for the Tensor 1D struct. And the type of the output, basically for this function, is going to be a one-dimensional tensor. So we're adding a 1D tensor plus some scalar, and we're getting back a 1D tensor. So to actually tell Rust how we want the addition to go, we're going to create a new function called add, which is going to consume the tensor that's being added, as well as basically the right-hand side of the addition operator, which we know is going to be a float 32, and we're going to return our one-dimensional tensor. So the first thing that we want to do is we want to allocate memory out on the heap to hold basically this new tensor that we're creating, right? So let's create a new mutable tensor called elements, which is just going to be our vector of float 32s. This needs to be like this. And then we're going to use this with capacity method to basically say, okay, when we go out onto the heap and we allocate memory for this new vector, we only need to allocate enough memory to hold the number of elements in our input tensor, right? So whenever you add a scalar to a tensor, the dimension doesn't change. You get back exactly the same size that you started with. So we already know how much memory we need in order to do this operation. I'll explain a little bit towards the end of the video why memory management with vectors really matters in Rust. But for right now, this is a good example. So then what we want to do is we want to go through each element of our original tensor. And we want to push basically the sum of that element. So this would be self.elements with our right-hand side. So we're going to iterate through T1. We're going to get the first element, add 2, and then we're going to push that to our new vector out in memory. Then we're just going to do this all the way down. And then the last thing that needs to be done is we go ahead and actually create the new tensor here. So elements is going to be our new elements array, and the dimension is going to be the same as the dimension of the input tensor. Now, if we do a cargo run here, you can see that we're printing out T2, which is exactly what we would expect. So now that we've kind of seen the common design pattern that we're going to be using to build out our tensor operations, it's time to start doing these really quickly. In order to kind of facilitate this, we're going to split our code base up now so that we don't have a bunch of operations in the same file that we have our tensor definition and the same file that we have our tensor methods. Like, that's a lot. So we're going to split it up into this tensors.rs file. This will hold the definitions and methods for our 1D and eventually our 2D tensors. And then we have ops.rs, and this is where we're going to hold all of the definitions for our tensor operations. We mentioned before that basically we made the design decision to make this library really only compatible with 32-bit floats. And I kind of said the reason for that was Rust. That's the short version. Here's the long version. So here we know that this works, right? We have the code to basically add a scalar to a tensor. Right now we're treating this 2 as a float because of this dot. If we get rid of this and now we treat it as an integer, if we try and compile and run our code, we're going to get an error. And the reason is that Rust is basically saying, hey, you defined addition for float 32s, but you didn't define it for integers. Now we know that you can add integers and floats, but Rust is really particular about type checking. Like, Rust wants you to be explicit about absolutely everything. And so if we wanted to actually implement our original idea where we would have tensors that could be floats or integers, we would have to basically do double our work to write methods for integer tensors and then float tensors and then addition operations between float tensors and integer tensors. Like, it just adds a multiplicity of complexity to the project. So this is why we did what we did. And from here on out, we're just going to basically define tensor operations for float 32s as well as between 2 tensors. So now let's go ahead and let's implement addition between 2 tensors. Once we have this general pattern, then basically we're just switching out the operations once we get to subtraction and multiplication. So let's go ahead and just duplicate our code that we had before, except now we're going to be replacing our mentions of float 32 with one-dimensional tensors. So this is a tensor. Okay, we're still going to be allocating memory in the same way, but we need to be just a little bit careful here in how we do this. If you're adding 2 tensors together, it's really important that the tensors have the same dimension, because if they don't, then your addition isn't really defined. So we just need to put a check in for this, just to kind of confirm for ourselves that this addition is even possible in the first place. So if the left-hand tensor does not have the same dimension as our right-hand tensor, then what we need to do is we're going to panic. And in panicking in Rust just means we're going to raise an error. And this error is just going to say, tensors must have equal dimension for addition. The pattern from here is exactly the same as what we had before, except we need to access the elements vector in our right-hand side tensor and add that to the elements of our left-hand side. Going back into main now, for kind of the first test that we want to run is we want to try and add together tensors of different length. So in this case, T3 has a dimension of 3, T2 has a dimension of 2. If we do a cargo run on this, it doesn't raise any like red errors in Rust, but you can see here that the thread main panicked at this point in our code. Tensors must have equal dimension for addition. So our code didn't actually end up running, which is good. That's what we want. If we get rid now of the back end of T3, this should compile and run with no errors and print to the console. You can see that it does. So I went ahead and I implemented basically all of the other one-dimensional tensor operations here. The reason why I did this off screen is because subtraction and multiplication over 1D tensors is exactly the same as what we did for addition. There's no difference. The only difference is the operation that we're applying to each element of the input tensors. So really not that much going on here. So I've written some test cases here for our tensor ops. I may implement more rigorous testing for this as we go, but probably that's not going to be something I'm going to put into a video. It'll just be more to check ourselves as we continue to build out the package. But let's go ahead and let's run our code. We can see that each one of these test cases compile and run, which is nice. I will kind of leave it as an exercise if you want to pause the video here and check out that each of these results is actually correct. So now I'm in our tensors.rs file. I want to implement just a couple more methods for our 1D tensors to make creating them kind of easy for a couple different use cases. So the first one, the first method that I want to implement is a method called random. So here is what our random method is going to look like. We're basically going to provide a minimum and then a maximum, and then a number of dimensions that our output tensor should have. So this is usize, and we're going to return a one-dimensional tensor. Now, initializing tensors randomly is something that's actually quite important to do in a library like this. Once we start doing gradient descent for, let's just think about like a linear regression, right? We do gradient descent, we're training the linear regression. Probably we want to initialize the coefficients of that regression to be random rather than 0. This is also very common when it comes to training neural networks. Oftentimes the weights and biases are not all initialized at 0, and the reason for that is because of the way that the derivatives of all of those parameters with respect to your loss function behave when everything's at 0. It all gets very unstable and messy, and then your gradient descent doesn't converge. So random tensor generation is actually really quite important. The way that we're going to do this is first we're going to get the range between our minimum and maximum. So let range, this is going to be a float 32, which is our max minus our min. We're going to apply min-max scaling here, but that'll come at the end. The next thing we need is a mutable vector, just like we saw in the ops implementations, where this is going to be a float 32, and it's initialized only to hold the least amount of memory that we need, basically. So capacity here is going to be dim. The next thing that we need to do is we need to instantiate a random number generator. To do this, we're going to use the rand crate, thread RNG here. So to do this, we're going to use the rand crate. It's true that rand is not technically in the standard library, but it's basically DLC for the standard library, so I'm not going to worry about this too much. It's pretty close. So what we want to do is for each element in our new elements vector, so for I in from 0 to dim, we're going to create a new float 32R by generating a random number between 0 and 1. So this is rng.gen. And because we've initialized r to be a float 32, this automatically is between 0 and 1. The last thing that we need to do is push this random number into our new elements vector, but we're just going to apply min-max scaling. So what min-max scaling looks like is we take our random number, we multiply it by our range, and then we subtract the min. You can think about this for a second to kind of convince yourself that this is actually correct, but you can convert a random variable 0 to 1 to a random variable between any arbitrary min and max with min-max scaling. So the last method that we're going to implement here is linspace. Linspace, basically the idea is you're going to generate a tensor where the elements of the tensor are between a min and a max, but the elements are evenly spaced between that min and max. So instead of rand, where it's just random between a range, now your tensor is going to have the first element is the start of your range, the last element is the end of your range, and then you evenly divide up everything in between with the remaining elements. That's a little maybe clunky of an explanation, but the implementation is pretty straightforward. So for linspace, we're going to have start, and this is a float 32. We're going to have an end, which is also a float 32. And then we're going to have dim, which is going to tell us how many steps basically are going to be in here. And that dimension is going to be a usize. This returns a one-dimensional tensor. So the first thing that we should do here is we should actually define like what the step size should be for a given start, end, and dimension. So let's let step be a float 32. And this is going to be equal to the difference between start and end. And we're just going to assume that end is greater than start. So we'll do end minus start. And then we have to divide that range basically by our dimension as a float 32. And then we need to go one less than that. And the reason is because the start is the first element of the vector and the end is the last element of the vector. So there's one less step that's actually going on in there. So we have to subtract that one from dim. Now all we need to go ahead and do is just iterate through our vector. So let's copy this up here to actually instantiate the vector, paste it, and then for I in 0 to dim, we're going to take our elements vector and we're going to push onto it the value of start plus I as a float 32 times our step size. Okay, so the first element is going to be start plus I, which will be 0 times our step size. So the first element is start. Then each subsequent element, we need to add an additional step compared to the previous one. So that's kind of where this logic comes from. And then the last thing that needs to happen is we just need to return our 1D tensor with elements as elements, and then dim as the dimension. And I just realized that we missed this up here. So let's paste that, and we should be good. So the last thing for us to do here is to just test these methods and confirm for ourselves that they work. So let's start with the rand method. So we're going to implement a 10-dimensional tensor where each element is random uniform between 0 and 5. So if we do a cargo run, here is our 10-dimensional tensor, and you can see that each element here is in fact between 0 and 5. You can generate a couple more to see that it goes up to 4, but never above 5. The next thing to test is linspace. So let's do a cargo run. And here you can see the first element in the tensor is 0, the last element in the tensor is 5, and there's kind of 10 elements in the tensor in total. So this is pretty much everything that I wanted to do in this video. In the next video, we're either going to do gradient descent with linear regression using this library, since we have pretty much everything we need, or we may go back and tweak the tensor struct itself. I've been reading up a lot on the way that PyTorch actually implements tensors, and it implements tensors of any dimension is just one long chunk of contiguous memory. And then when you slice it, it just returns back kind of views and chunks in that memory. That seems really fun for me to do, so we may kind of backtrack a little bit in the next video, but we'll have to see. Anyway, that's it.